This next video shows you how to find volumes when the region is rotated about the y-axis. And this is not the usual case. We try to rotate things about the x-axis, but they could also ask you to switch your perspective and rotate things about the y-axis. So then we have the example, find the volume generated by rotating the region bounded by the functions below about the y-axis, and the functions are y equals 1/4 x squared, x equal to 2, and y equals 0. And one thing we should note is that we should know how to graph these. This is just a parabola, and x equal to 2, that's a vertical line, and y equals 0, do you know what that is? It's a horizontal line, but it's a very specific horizontal line. It's the x-axis. So we want to graph those, look at the region that is bounded by those functions, and then think about the rotation. So let me think about the picture of that. So this is what the functions look like once you graph them. Of course, you don't have to be very precise. You're not getting any extra points for the picture. But it has to be clear enough where it helps you to set up your integral. So 1/4 x to the second, I know that that is a quadratic. I know it opens up, and I know that it has 0, 0 as the vertex, because this is basically the parent function, and the 1/4 is only stretching it or compressing it vertically. Nothing else is happening. X equal to 2, that's my vertical line. Y equals 0, the x-axis. Now I can see that the bounded region happens to be only in quadrant 1. So this is the region that gets to be revolved about the y-axis. I've also signaled here that I'm revolving about the y. That's to make sure I get the right integrand. And I don't really need this left half. But then, because when I rotate, I'm going to create a mirror image of this, then I think I'll leave it here. I think I'll use that when I'm ready to draw the discs. And that's the next thing we need to think about. How do you draw the discs? I hope you can see that these are going to be now horizontal discs, and they're going to stack up on top of each other vertically. And what I want you to think about next is, how would I draw them? I also hope you can see that you need to use the washer method for this example, because there will be some empty space. And the empty space comes from this space here that's not shaded, and it's going to be rotated as well. So there's going to be a hole inside of my solid. Okay? So now think about it. How would you draw these two discs? One of the discs has to contain the entire solid, and the second disc has to be a smaller one, and that's the disc that'll produce the empty space. Okay? Well, I hope that when you think about the discs and you see my sketch coming up, that we agree on the way it looks. So here they are, the two discs. The yellow one is the bigger disc. That'll cover the entire volume. And notice again, we are going from the axis of revolution to the original functions. And remember that this left-hand side was not part of the original region. That's why I am not drawing the radii toward that side. Instead, from the axis of revolution to the actual function, where the region was first bounded. And the yellow disk, it's going to produce the entire volume. And can you imagine, can you see the rest of the disks that are the same size as the yellow one? They're just stacking up on top of it. And it goes all the way up here. And that'll produce the volume. Now the green disk, that's the one in charge of creating the empty space for you. That's why it goes from the axis of revolution to the blue function. And We just need to subtract them both, their volumes, and then integrate and think about the limits of integration, and then we have solved the problem. Okay, so let's think about what the big radius should be, capital R of x. And can I convince you that this distance is just 2? And it doesn't matter where I take the disk. If I drew the disk up here, it would still, if I wanted to cover the entire volume, it would still be radius 2. So that's a simple one to figure out. It actually will create it's going to create a cylinder. So now the next question is, well, what about the little radius? What's that going to be? I hope you can see that the little radius, the empty space that it'll produce, it'll look like a bullet of sorts. And so then the remaining volume would be like the casing of the bullet, I guess. And what is the distance for this little radius? This distance here. You have to think about it in terms of make it easy for you, make it simple. The distance here is exactly the same as if I were down here and I just brought this radius down. So this distance here is the same as that distance there. Okay? And the main thing here is that this distance is a horizontal distance. The distance from here to there, it's horizontal. And because I don't know exactly what the distance is, but I know it's a horizontal distance and it's along the x-axis, then I know I can call the distance x. Because it's just some random location for that disk. So then I would have to say that this is x. Except because my disks are now stacking up vertically, then these are no longer functions of x, both of these. This is actually wrong. Instead of calling it r of x, I should be calling it r as a function of y. Because my rotation now happens to be about the y-axis. And so it's little r of y. And I know the distance is x. But what is x? I have to have it as a function of y. Well, for that, we go back and we remember the function is 1/4 x to the second. And so what we have to do now is solve this equation for x. So I can multiply both sides by 4 and say 4y is equal to x to the second. Then I could take the square root of it and say x equals plus or minus the square root of 4y. But out of the plus or minus, I know I'm in quadrant 1. And I know that this x distance is a positive distance, isn't it? So then that tells me that I'm going to use the positive square root of 4y. Of course, I can simplify things and say the square root of 4 is 2. So this is 2 square root of y. And because I know what's going to happen next, there's going to be an integral at one point. Then I rather write it as x equals 2y to the 1/2. And that's easy to integrate if I need to. So again, this x, it stands for any x. And so my x distance here, which is the same as my radius distance here, has to be 2y to the 1/2. And that is a function of y. And now I can write it down here. Make sure you understand what just happened there. And again, the main idea is, can you find the radii, especially when you have two, the volume and the empty space? Can you figure out what the radius is? If you have a good picture and you know how to label it, then that'll help you. So now here's the general template for the volume of the solid. pi times the integral, big radius squared minus little radius squared. Please remember that each of the radii individually get to be squared. And another thing to pay attention to is that this is an integral with respect to y, and that should remind you of two things. Why is it with respect to y? One very clear thing, you can see that the thickness of the disks are now vertical thickness. And that little thickness would be dy. The same for the green disk. Its thickness is vertical, and it's a very small amount, and we call that amount dy. And the other thing that you should recall if you see dy is that this region was rotated about the y-axis. So if it's about the y, you should have a dy. Now we are concerned with what are the limits of integration. And one common mistake is to say, oh, the limits are from 0 to 2, or from -2 to 2, because those are the only numbers we get to see at this point. But remember, if this is dy, then we actually have y equals and y equals for the limits of the integration sign. And so now you have to think about it in terms of y. Another thing to consider when you think about the limits is which way are the disks stacking up against each other. These disks are stacking up vertically. So you have to figure out from what point up to what point are they being stacked up. And so I can see down here the y is 0. That helps me with my lower limit, 0. And well, what about up here? What is the number where we stop the accumulation of the disks? Well, it would have to be wherever this line meets the function. Wherever this line meets the function. And to figure out this y, then, we take x equal to 2 and we plug it into the function and we figure out what the y is. And so I'll do that right now. X is equal to 2, so I have y equals 1/4 x, which is 2 squared. That would be 1/4 times 4, which equals 1. Y equals 1. So then my disks go from 0 all the way to 1. And so 1 is the upper limit of integration. So now I've just replaced the values for the capital R and the lowercase r. And when you do the math, it's actually a simple integral, especially here. This is just a 4, and 2y to the 1/2 squared. You square the 2, you get a 4. You square y to the half, you multiply the powers, and you get y to the first, or just y. And then integrating is quite simple. 4y minus 2y squared from 0 to 1. And I'll leave you to double check my work. I got 2 pi, which is a nice number. Now remember, this is the volume of the solid you get by rotating this region here about the y-axis. And so quite an impressive result, because I don't even know the name of this object, but I can tell you what its volume is. So this is an example of revolving something about the y-axis.